All right, so this is a review of reactions, which is chapter 4 in the beginning part of chapter 20. So first you have to go through the types of reactions that you can have. The first type of reaction is synthesis. Right, this is a little more complicated on the AP level than it was on the previous chem level because you're not just taking two elements and putting them together this time, but you know that if you do have a metal with a nonmetal, you're going to make an ionic compound. If you have two nonmetals, you're going to make a molecular compound. But the synthesis reactions that are important here that come up a lot in AP are when you are taking a nonmetal oxide or a metal oxide and putting it in water. So a nonmetal oxide like nitrogen dioxide, you put that in water. Anytime you put a nonmetal oxide and water together, you're going to get an acid. Right, so that's a pretty common one, right? Carbon dioxide makes carbonic acid. That one everybody should know. AP College Board likes carbonates a lot. It likes carbonic acid a lot. So those are common ones that come up. When you have a metal oxide like sodium oxide, and you put that in water, you are always going to get a base from that. Right, so this is going to make sodium hydroxide. All right, so anytime you have a metal oxide, you're going to get a base. Anytime you have a nonmetal oxide, you're going to get an acid. So those are the other types of synthesis reactions that tend to show up a lot. After synthesis, we know that we have decomposition. All right, the decomposition is taking stuff apart. So not only do you have the reverse of these, which can happen, but there's also a couple other decomposition reactions that are pretty popular and pretty common that College Board uses and colleges use. Anytime you have a carbonate that decomposes, you're going to get a metal oxide and carbon dioxide. So that's a very common one. Anytime you have a carbonate, you're going to get a metal oxide and carbon dioxide. So whatever the metal is here is what's going to be the metal in the metal oxide. Another one is if you have a hydrogen carbonate. All right, if that decomposes, you're going to get the metal oxide. You're also going to get water and carbon dioxide. All right, so you're going to have to account for that. And then the last one that comes up that's not just a reverse of a synthesis that comes up a lot is when you have the chlorates. So like potassium chlorate, the decomposition of that one is going to give you your salt, your potassium chloride, and oxygen. And obviously you got to do some work to balance that all out. All right, so there's a sample of decomposition reactions. Now, we haven't talked about net ionic equations because we don't have any ions here. Synthesis and decomposition reactions tend to be hot, and because they tend to be hot, whether you're putting the energy in the case of decomposition or the energy is coming out in the case of synthesis, that heat is going to remove a lot of the water that's present while you're doing it. So you don't have to worry about dealing with ions because nothing can dissolve here. So this is all going to end up being situations where you're going to make a product that tends not to be ionic. Now, I know that we have an issue here, but this is usually talking about atmospheric conditions where you're going to have that. So you have to read the conditions of the question to figure out whether you're going to have to write these as ions or not. So they're going to let you know that you're going to have excess water. That lets you know then that it's going to be ionic. And if it's going to be ionic, then just break it up into the ions. All right, but what you have to remember is that the only type of reactions you're allowed to write are net ionic equations. They don't care about the full reaction. They care about net ionic equations. Over the course of the year, I've seen lots of bad equations written on quizzes where people obviously have gotten rusty with net ionic equations. So when we get through the next two types of equations, then hopefully that will help you get some of that rust out from the net ionic equations. So let's get these out. I guess real quick, I should just mention as a review, so I cover all bases, combustion. I think the most common thing that comes up with combustion is that people forget about the oxygen as a reactant. So if I'm going to combust something like glucose, I got to remember that it's plus oxygen, and I'm always going to make carbon dioxide and water. And again, we talked about that in the previous one when we talked about empirical molecular formulas, that this excess oxygen that comes into there is the reason why we can't just do a amount of oxygen over here and attribute all of that to the glucose if we were looking for the formula for it. The extra oxygens that are over here, a lot of them came from here in addition to there, right? Twice as many oxygens came from this excess oxygen provided than what was in the glucose to start, right? But just remember this part in combustion, because a lot of times they don't say it, so you're just supposed to know that if you're going to combust any substance, that means you're going to add oxygen to it. All right, so guess we have 3 left to do. One is the acid-base reaction. So this is going to be net ionic whenever you write this. And so it depends on what type of acid or base you are dealing with. So if you're dealing with the strong acid, strong base situation, like where you're going to react, I don't know, we'll put sulfuric acid plus calcium hydroxide. So you have that strong acid, strong base situation. When this happens, you're just going to end up getting your products of calcium sulfate and 2 water molecules. But what you have to remember is, since this is aqueous and this is aqueous and this is aqueous and that's water, that your net ionic equation when you're dealing with strong acids and strong bases is simply H plus OH minus yields H2O. And that's your whole net ionic equation, because the calcium sulfate is going to be soluble because these were both strong acids and bases. So we know that our product of that is going to end up being soluble. So that is what you're going to end up with net ionic for strong acid, strong base. Okay, so this is strong, strong. All right, but what if it's weak, strong? All right, so that's always the typical acetic acid. Plus, I'll just do sodium hydroxide. We know our product of that is going to end up being sodium acetate and water. All right, so obviously we're going to have the H plus OH minus yields H2O as part of our reaction here. However, the thing that we have to remember is, since the acetic acid is a weak acid, that we actually have to write that in our net ionic equation. You are not allowed to split that up. And then on the other side, we have to have the acetate ion here. So the only spectator here ends up being the sodium, because that is your cation in a strong base. So that's going to not change. It's going to be aqueous here. It's going to be aqueous there. So when you're dealing with your weak acid or weak base, you have to remember that you can't separate that in the net ionic equation. You have to write it together. When you write it together, then you have to remember to bring that ion over to the other side. So your net ionic equation ends up being that. Okay, so hopefully that's a reminder of what happens when you're dealing with strong acid, strong base. You get this reaction. Weak acid, strong base would give you this. If it was a strong acid with a weak base, you'd have the H plus by itself, and then whatever your weak base is would have to be written together over here, and your cation would have to be written over there. So an example of that would be like HCl plus FeOH2 or 3, doesn't make a difference. That's going to give us 3 water molecules plus iron 3 chloride. So when we write the net ionic for that, now you're going to have H plus and you're going to add to that the whole FeOH3, because we can't dissociate that since it's a weak base. And so on this side, we're going to end up with the 3H2O, and we're going to have to write Fe3+. Okay, and that's then going to be the situation for a strong acid, weak base. All right, so there's the acid-base reaction. So the difference in these reactions is that you're taking your ions and you're making water out of it. That's your change of phase that makes the acid-base reaction happen. And remember, if AP tells you that there's a reaction, there's a reaction. They're not trying to trick you. They're not trying to make you double check that the reaction should occur. If they tell you it's happening, it's happening. So there's your acid base, which definitely requires net ionic equations. All right, the next type of reaction is precipitation. Okay, precipitation reaction is when you're dealing with aqueous substances, you put them together, and it gives you some sort of solid. So you take sodium sulfate and barium chloride, and you put them together, and we're going to get barium sulfate plus sodium chloride. All right, so there's your old-fashioned double replacement reaction. And so now that we have this, in fact, the acid-base were double replacement reactions too, back in your previous chem course. But now that you have this, we have to think about what's ions and what's not. So your reactants are going to be aqueous. The barium sulfate is going to be the solid here. All right, so you have to go back and review your solubility rules. So remember to do that. So since these are aqueous and that's our solid, it means that our net ionic equation is going to be the ions that it takes to make that. So it's going to be barium plus sulfate ions yields barium sulfate. And that's your whole net ionic equation. So that's all you have to do for precipitation reactions is figure out what your product is that's insoluble, or your product that's going to be the solid. And then it's always the two ions that are going to make that. And that's it for precipitation reactions, right? So the hard part is knowing what the solubility rules are, knowing that sodium compounds and halogenated compounds tend to be soluble, with the exception of the heavy metals like lead and mercury, right? Silver, those things are going to be insoluble with halogens. But the alkali metals are always soluble unless you stick them with oxygen and sulfur. Your nitrates are always soluble. Your carbonates usually aren't. Your acetates are usually soluble. You know, you should know those ones that are, yes, this is pretty much soluble all the time. And then you can usually use that information actually to figure out which one isn't. I mean, if you look at this, you know that sodium chloride is soluble. If you don't know that, then you really haven't done much work in your solubility rules. Once you know this is soluble, then that can't be. Makes it very simple. Right, so rather than figuring out all the things that are insoluble, sometimes the best thing to do is to figure out all the basics of what is soluble, and then you can figure out what's insoluble by process of elimination. All right, so there's your precipitation. So that leaves us with only one left, and the last one that's left is your redox. Right, your oxidation reduction reactions, which we came back and reviewed again. You had the very basic ones, which are dealing with metals and nonmetals. So some of these cross over with synthesis reactions. You know, it's hard to differentiate these sometimes. It depends on what you're trying to do with it. So we know that if we have sodium metal plus chlorine as a nonmetal, pure nonmetal, we're going to get sodium chloride. All right, if we do our net ionic equation for this, well, there really kind of isn't one, but if we do our half reactions for this, what we have is we have our sodium going to sodium ions. We have our chlorine going to chloride ions. In the process of doing that, which we have to do this twice, in the process of doing that, we know that the sodium has to lose 2 electrons, 1 electron for each sodium, and we know that chlorine has to gain 2 electrons to get there. So depending on what phase your product's in is going to determine whether you are going to write these as ions or not when you make them. But note that this is your oxidation, because this is the one that has an increase in charge. When your charge goes up, that's oxidation. And this one's your reduction, because you went from 0 charge to a -1 charge. So that's the one that had its charge reduced. Okay, so there is your simple redox situation. All right, but we also know that we have harder redox problems, the more advanced ones. And so let me do one of those. Actually, I was going to do it underneath, but I want to make sure I have enough room. So I'm just going to get rid of this. All right, so we can have something like potassium dichromate plus chlorine to see what we get out of that. All right, so things to remember about these advanced redox problems. First of all, it might look like a single replacement reaction or a double replacement reaction when you start, and you have to get that out of your head right away, because these can never be single replacement or double replacement. When you have a dichromate or a chromate or a permanganate, you know that you're dealing with an advanced redox problem and you have other steps to do. So if we can't just simply do a single replacement or double replacement here, then what do? Well, we look at our oxidation and reduction halves individually. So I'm going to start with the oxidation. So the oxidation is going to have to be, I did this backwards. This has to be maybe sodium chloride. Let's do that. All right, so the oxidation has to be where your charge is going up, right? So that's not as clear here, but what we usually can do is we usually can figure out what some of our spectators are right at the beginning when we're looking at these. We know which substances are always soluble. We know that these things are always going to occur in water. And so the things that are always going to be soluble in water and therefore will never get involved in oxidation reduction reactions are always going to be your alkali metals. So a lot of times they don't even bother writing those things. They just take them out right away and they just say, okay, you have chromate ions with chloride ions. Okay, so we got rid of the potassium and the sodium because we know those are going to be spectators. So let's do our reduction first. Our reduction is going to be related to the chromium here, because we know that if we figure out based on the oxidation numbers here, the oxidation number of chromium, it's going to come out to be a pretty high number. So oxygen is a -2. There are 7 of those, so that gives the oxygen as a total of -14. Overall, this ion's allowed to be left with a -2 charge. So since the ion's allowed to have a -2 charge, that means that the chromium has to be +12 to make it work out, right? A +12 from the chromiums, the -14 from the oxygens leaves us with a -2. Since we have 2 chromiums to do that, what we'd find then is that chromium is really a +6 here. All right, so now the question is, or the other part of this that helps you recognize that you have an advanced problem, is it tells you whether your solution is acidic or basic. So I'll just go with this is an acidic solution. All right, so since it's an acidic solution, what we need to know is what charge our metals are going to want to go to. For chromium, its most common charge is a +3. Chromium and iron are always a +3. Manganese and nickel and cobalt are going to be +2s, and copper is going to be a +2. So since this needs to be a +3, our reduction needs to leave us with chromium as a +3 charge. So yes, chromium is a +6 here, but you're not allowed to pull this out of the dichromate ion. Your substance that's being reduced is the whole dichromate ion, so you have to write that. Cr2O7 with a -2 charge. Now, we have 2 chromiums that are going through this process, which means I'm going to end up with 2 chromium ions over there. All right. I'm going from a +6 to a +3 for each one. So each one then has to be gaining 3 electrons. And since I'm doing that process twice, that means I have to gain a total of 6 electrons to make this work. Okay, I'll say that again. The chromium is a +6 here, going to a +3. So each chromium has to gain 3 electrons to get from +6 to +3. But since there are 2 chromiums in here, I have to do that process twice. So since each one's gaining 3, doing it twice means I have to gain 6. All right, so now I have that. But what I haven't done yet is I haven't balanced the oxygens. I have to do something with the oxygens. The way I balance that is by adding water to the other side. So since I have 7 oxygens there, I need to add 7 water molecules over to the other side. And if I'm going to add 7 water molecules to this side to balance the oxygens, I have to balance the hydrogens. So 7 times 2, I have 14 hydrogens. So over here, I have to add 14 H pluses. Right? And since it's an acidic solution, it's okay for me to add the H pluses here. So now that I know that this is my reduction, now I can go and do my oxidation, which is going to be my chloride oxidizing, having its charge go up. Well, what is the next charge up from -1? Well, it's 0, which means what I'm going to end up doing is I'm going to end up making chlorine, which means I'm going to have to do this twice. And each one is going to have to lose an electron to do this. So each one's going to lose an electron, but since I'm doing it twice, I'm going to have to lose 2 electrons. Okay, so this process gives me 2 electrons every time I do it. This process requires 6 electrons every time I do it. So this isn't going to work, because in order for a redox reaction to occur, we know that the number of electrons lost in the 1/2 reaction has to equal the number of electrons gained in the other half reaction. So I'm going to have to do this top reaction 3 times. I'm going to have to make this 6, this 3, and then it makes this 6. So now when I'm all done, when I add down, this is going to give me finally my net ionic equation. So 14H plus 6 Cl minus plus Cr2O7 2 minus yields 3 Cl2 plus 2 Cr plus 3 plus 7 H2O. So there is my complete net ionic equation for being in an acid situation. Okay? Notice this looks nothing like a single or double replacement reaction. Like I said earlier, you can't do that. You have to do it based on the half reactions. And I picked a pretty complicated one, right? You should know very well the one we did in the lab for the redox titration. The 2 of them we did there, actually. The iron with the potassium permanganate and the oxalate with the potassium permanganate in that one as well. All right, so this is a pretty complicated one. So what happens if we put it in the base? Well, if we're going to put it in the base, then we can't have any acid ions in the solution. So all I'm going to do is I'm going to take my acid out of the solution by adding 14 hydroxides to that side. I know, it looks like HOH. Let me fix that. 14 hydroxides to that side, and I'm going to add 14 hydroxides to this side. Now, when I do that, this is going to make a total of 14 water molecules, which is fine, except I don't need 14 water molecules because I have 14 water molecules over here, and I have 7 over here. So since they're on opposite sides, those things can cancel right away. So what I'm really going to end up with here is just 7 water molecules. Now everything else is the same. I just bring it all down. 6 Cl minus plus Cr2O7 2 minus yields 3 Cl2 plus 2 Cr3 plus 14 OH minuses. And that's what would happen if this reaction was in a base. Now, chances are that if it's in a base, this could be something different. This could be chromium oxide or chromium CrO2 or something like that. So they usually will tell you this if it's in a base solution, but if not, they usually, in the past actually, would accept this as well as your answer if they were just asking you to write the net ionic equation for the redox reaction. Okay, so that's a review of all the different types of reactions we did, and that's it for Chapter 4 and Chapter 20.